My dear students, I welcome all of you for today's session on design and analysis of algorithms. In today's session, we will have a discussion about introduction to divide and conquer. It's a continuation of introduction. In previous session, I given you introduction, part of the introduction. Introduction was not able to finish. Okay. We are just seeing in previous session I given some example problems, okay, to justify what actually divide and conquer strategy means. Okay, we have seen a generic algorithm. Okay, we have seen a generic algorithm for divide and conquer, and at the last of the previous session, we are discussing about time complexity for any divide and conquer algorithm. Means, what is that standard representation? Okay, standard equation to represent time efficiency of any algorithm or any solution based on divide and conquer strategy. Okay, in today's session, okay, I will introduce you to a master theorem. Okay, a master theorem is nothing but, okay, it gives, it computes the time efficiency for any algorithm that is implemented using divide and conquer strategy. Okay, clear? So what actually we are going to discuss, the core of this session is Master's theorem. So Master's theorem is to determine time efficiency of any algorithm, okay, designed using divide and conquer strategy. Clear? So now coming to agenda of this session, the first see, because I said I was not I was discussing computing time of divide and conquer algorithm at the last of previous session. Got it? There, what I've seen, we have seen a recurrence relation for this time efficiency. Clear? Clear? We have seen a recurrence relation, okay, represents time efficiency for any divide and conquer algorithm. Clear with this? The same recurrence relation now I will review here. Okay, I will review because I want you to make that recurrence relation, okay, you to become familiar. Then we will proceed to master theorem. So, clear. See, in a previous session, what I winded with the recurrence relation, right? So now you need to set up a recurrence relation with initial condition. So later, what you should do? You should solve that recurrence relation using your discrete mathematical structures concept. So after solving recurrence relation, you will get an exact count for the basic operation. Now, when you have an exact count for basic operation, then you will see to what type of efficiency class that basic operation count belongs. Is it? Then you will represent the asymptotic order of growth for that particular problem, particular algorithm. Clear? So the advantage of master theorem here is that master theorem, using theorem here, we we need not have an initial condition. Okay, we just we can obtain a recurrence relation for the divide and conquer algorithm. Then you need not have to solve that. The main advantage is that you need not have to solve recurrence relation in master theorem. Okay, Using master theorem without solving recurrence relation, we can tell what is an order of growth of that particular divide and conquer algorithm. Now, hope you are clear with what the agenda of this session means. In this session, what I wanted to tell you is that I need to explain you about master theorem. So master theorem is nothing but theorem to analyze efficiency of divide and conquer algorithm. Okay, sorry, efficiency of divide and conquer algorithm. Clear? So I mean, in previous session, okay, let me show you the slide. So in this slide, what you can see, the recurrence relation, just observe the recurrence relation. Clear? Okay. Uh, Recurrence relation that computes time efficiency of a divide and conquer algorithm. Clear? So now you have given an initial condition too, right? So what you should do actually, using your discrete mathematical structures, you need to solve this recurrence relation. Clear? Means don't look at the last one. T of n equals a T of n by b plus f of n. Okay, that's a recurrence relation where n is large, and T of n equal to g of n when n is small. This is an initial condition. So clear? I repeat. Okay, for any divide and conquer algorithm, the general recurrence will be of the form for time complexity. T of n equals a T of n by b plus f of n. Means a problem with size n is divided into a subproblems, each of size n by b. Clear? A problem with size n is divided into a subproblems. Got it? Each of size n by b. Clear? So to determine the time, taken, okay, to determine time taken, okay, to get the final answer for the problem, okay, we need to consider time. Got it? To get answer for each of the subproblem, right? I mean, T of n is a time to get answer for the main problem. That is final answer for the main problem. But what I said, this subproblem has been divided into a subproblems of size n by b. Clear? Means, I mean, I need to consider into account the time taken to get answer for each of the subproblems, right? I need to consider into account the time taken for getting answer for each of the subproblems. Clear? So T of n by b represents time for getting answer for one subproblem. So there are how many subproblems? A subproblem. Clear? So the time for getting answers for all these subproblems is a T of n by. Clear with this? So next, now I considered into account time for getting answers of all the subproblems. Later, what we'll do in conquer stage, the answers of all the subproblems will be combined. The answers of all the subproblems will be combined to get final answer. So you need to think very clear. Means combining answers of the subproblem to get final answer also incurs time, right? Clear? Means in order to combine the answers of subproblems to get final answer, a time is incurred, time is involved, and let this time be f of n. Clear? So now what is f of n? The time for combining. Of course, f of n involves time for dividing also. Means I need to consider the problem with size n got divided into subproblems. So dividing the problem into subproblems also has time involvement. Finally, combining the answers of all the subproblems to get an final answer also involves time. And this time is represented by f of n. Clear? So, in general, what I can say, divide and conquer algorithm. Okay, in general, for divide and conquer algorithm, the time efficiency, I repeat, in general, for any divide and conquer algorithm, okay, time efficiency will be represented by recurrence T of n equals a T of n by b plus f of n. Clear? Got it? In general, for any divide and conquer algorithm, time efficiency T of n is nothing but a T of n by b plus f of n. Clear? And we'll have initial conditions. This thing I've explained in detail previous session, so I don't want to repeat further because I won't be able to complete the agenda of today's session. Okay, so now, and while discussing mathematical analysis of recursive algorithm, remember there are 5 steps. So in the fourth step, let me tell you, in the fourth step, okay, while discussing mathematical analysis of recursive algorithms, in the fourth step, okay, you need to set up a recurrence relation with initial condition. Clear? Recurrence with initial condition. Got it? For basic operation code. Now, using your discrete mathematical structures, you need to solve that recurrence relation. Then you will get a basic operation count. Once you have a basic operation count, you need to identify to what efficiency class it belongs. Clear? Then you can represent order of growth. Got it? So this is manually we should solve, and we need to identify the efficiency class. So to avoid solving recurrence relation and explicitly we can state the order of growth. Without solving recurrence relation, we can identify the order of growth. Without solving recurrence relation, we can identify order of growth. Got it? That is through Master's theorem. Got it? So coming to Master's theorem. See here. Let me say Master theorem. Okay, let me say here. I said for any divide and conquer algorithm, time efficiency is represented by recurrence what? T of n equals a T of n by b plus f of n. Okay, clear? You will be given a recurrence equation T of n equals a T of n by b plus of f of n. And now you are asked to determine order of growth. Now you are asked to determine order of growth. I mean, you need to tell whether it's a logarithmic, linear, n log n, quadratic, cubic, exponential, factorial. Now, how will you determine? Okay, so, and I'll tell you, I need to tell you, you are given only recurrence equation, you have not given initial condition. If you are given both recurrence equation and initial condition, you would have solved that. Then you would have got a basic operation. Then you would have identified what efficiency class. Clear? So, but now what I said, you are given only recurrence equation, but you are not given initial condition. Then we can't solve this because for the recurrence that keeps on going, there is no end for the recurrence. So now you need to take an advantage of Master's theorem. Listen, what I said, you are given only recurrence equation, no initial condition. Okay, but you need to identify efficiency class. So now what you need to do, take an advantage of Master's theorem. Okay, so look at recurrence equation. T of n equals a t of n by b plus f of n. Okay, now f of n, you check what type of function is f of n. Okay, check what type of function is f of n. Is it quadratic? Is it cubic? Is it linear? So and so. Okay, now check what type of function is f of n. What type of function is f of n? Linear, quadratic, or cubic, or any other. Now, say for example, f of n belongs to big theta of n power d. Okay, that f of n function is there, right? That belongs to big theta of n power d. Got it? So now, once you identify, okay, f of n belongs to some big theta of n power d. Okay, I mean to say you need to determine degree of f of n. So let it be d. Clear? Let d be the degree of f of n. I repeat, let d be the degree of function f of n. Okay. Then you, from the recurrence, you have what is a, right? Clear? You, from the recurrence, you have what is b, right? Also from f of n, you have what is d. Clear? So now you have the three values a, b, and d. Now you determine the relation between a and b power d. Determine relation between a and b power d. There are three possibilities: a less than b power d, got it? A equals b power d, a greater than b power d, got it? So based on these cases, if a is less than b power d, okay, then efficiency class is big theta of n power d. I mean t of n belongs to big theta of n power d. If a equals b power d, then t of n belongs to big theta of n power d log n. Clear? Suppose if a is greater than b power d, then t of n belongs to big theta of n to the power log a base b. Got it? So I repeat, here three values a, b, d. Determine relation between a and b power d. There are three cases: a less than b power d. If yes, then t of n belongs to big theta of n power d. Okay. Second case: if a equals b power d, then t of n belongs to big theta of n power d log n. If a greater than b, then t of n belongs to big theta of n log a, n power log a to the base b. Clear? So in note, I said analogous results hold for the big O and big omega notations too. I mean, in this definition, I've assumed f of n belongs to big theta of n power d, right? Suppose if I find f of n belongs to big O of n power d, or big omega of n power d, then in all these three cases, in place of big theta, I should use big O or big omega. Clear? So this is about Master's theorem. So here I need not have an initial condition. Clear? So I can explicitly Okay, state the efficiency class. Now, coming to advantage and disadvantage. So, what I said advantage, we can find solutions efficiency class without solving the recurrence. Of course, I said right, we need not have to solve the recurrence. There's no time involved in solving the recurrence. Looking at the recurrence itself, we can tell what efficiency class. So now, what is disadvantage of master theorem? So disadvantage of master theorem is that it doesn't give exact basic operation count. Exact basic operation count. See, while discussing mathematical analysis of recursive algorithms, okay, what fifth step says? Fifth step, what it is? Solve the recurrence. Clear? As solve the recurrence with make taking an advantage of its initial condition. Got it? Using my discrete mathematical structures concepts. So after solving, I was getting exact basic operation count. Got it? Clear? So exact in that analysis, I was getting exact basic operation count. Then I used to see to which efficiency class that exact basic operation count was belonging. Clear? Then I used to represent its order of growth. But in Master's theorem, I'm not solving at all, right? Recurrence. Clear? Because I don't have initial condition. Since I'm not solving the recurrence in Master's theorem, I'm not able to get, okay, I'm not able to get exact basic operation count. Just I can have an order of growth. Clear? So this is clear with advantages and disadvantages of Master theorem. So advantage is that we can find solutions efficiency class without solving the recurrence. Disadvantage is that it determines only order of growth. It does not give exact count of basic operation. Okay. So now let me solve some problems. Okay. I mean, let me give you some exercise problems. Okay. I will give you some recurrence relation in further slides. I will give you some recurrence relation. Okay. In further slides. You need to tell me, you need to solve, you need to obtain its efficiency class. It means in the further slides, I'm gonna give you some recurrence relations. Okay. You need to obtain its efficiency class. So now let me look at first problem. So exercise 1. Consider the recurrence equation for the number of additions A of n made by the divide and conquer sum computation algorithm. Okay. The main thing, just I need to look what is that recurrence. So what is recurrence? A of n equals 2a of n by 2 plus 1. Okay. And what I have asked to determine, find the order of growth of the function a of. Okay. So in place of t, I have just used a. That's it. Okay. T generic. A here represents the basic operation might be addition. So got it. So now recurrence is a of n equals 2a of n by 2 plus 1. Okay. So now what we need to determine? We need to determine a of n belongs to what? I need to determine a of n's order of. Is it logarithmic, n log n, linear, quadratic, cubic, exponential, factorial. So now, am I given initial condition? No. So if initial condition is not given, I can't solve. So I need to take advantage of what? Master's theorem. So now let me again map this A of n equals to A of n by 2 plus 1 with Master's theorem recurrence. So here recurrence is T of n equals A T of n by b plus f of. So in A and B, A and B in this case it is 2. And f of n in this case it is 1. So f of n, see in this case A and B both are 2. Yeah, the values, okay, lowercase a and lowercase b. Got it? It's 2. And f of n is equals to 1. So f of n in this case equals to 1 means it's a constant function. Degree of this f of n is 0. Very clear, right? You know, right? How to identify degree. Clear? So clear? So for this recurrence, when I compared map with the recurrence of divide and conquer, I found A and B with same value 2 and f of n equals to 1 indicates degree 0. D equals 0. Now what I need to do? I need to determine relation between A and B power D. So what is A? 2. B power D equals to 2 to the power 0 equals to 1. So A is 2, B power D is 1. So what is the relation between A and B power D? A is greater than B power D. Is it? So A is greater than B power D. So if A is greater than B power D, then which among 3 cases I need to choose? Like this. So A is greater than B power D means third case. Third case. Instead of T of n, there I will use A of. So that belongs to what? Big theta n to the power log A base B. Okay. So A of n belongs to big theta of n to the power log A to the base B. On substituting values for A and B, A of n belongs to big theta of n to the power log 2 base 2. So you can see, just check what is log 2 to the base 2. It's nothing but 1. So A of n belongs to big theta of n to the power 1. It means A of n belongs to big theta of n. So what is the order of growth? Linear. Got it? So I think you're very clear with this problem. Okay? It's very simple, right? Without solving, we can tell what is an order of growth. Yeah. So I think everyone are clear. Now let me have a look at second problem. Using Master theorem, find the order of growth of the function t of n equals to t of n by 2 plus. Okay. Now I think you have in mind that recurrence for divide and conquer. If not, let me compare this t of n with the recurrence of divide and conquer. Okay. The recurrence for divide and conquer in general is t of n equals a t of n by b plus f of. So when I compare, I find A and B equals 2. Okay, A and B equals 2. And in case of f of n, I have n. Got it? In case of f of n, I have n. So f of n is linear. So what about degree of this f of n? It's nothing but 1. Clear? N to the power 1 is n. N to the power 1 is n. Clear? So degree of f of n in this case it is 1. So clear? So now I have values A, I have value for B, I have value for D. Now determine relation between A and B power D. A equals to B power D equals 2 power 1 equals 2. So the relation is that A equals to B power D. So now A equals B power D, right? So now which case among 3 cases I need to choose? Okay. So now the relation is A equals B power D. Okay, now let me look at the cases of master theorem. Okay, A equals B power D means second case is T of n belongs to big theta of n to the power D. Listen, n to the power D log n. What was D there? 1. D was 1, right? So T of n belongs to what? Big theta of n power 1 log n. Here. T of n belongs to big theta of n power D log n. D is 1. So T of n belongs to big theta of n power 1 log n. That is nothing but T of n belongs to big theta of n log n. So clear? So think everyone are clear with this second problem. Okay. Now let me have a look at one more exercise problem. Using master theorem, find the order of the growth of the function t of n equals t of n by 2 plus. So t of n by 2 means it's nothing but 1 t of n by 2. So when you compare this with the recurrence of generic divide and conquer, what you will find? A equals 1, A equals 1, B equals 2. Clear? A equals 1, B equals 2. And we have C in case of f of n. So what is C? Is just a constant like 1, 2, 3, whatever. So there is no n, right? In f of n. F of n equals to C means f of n is a constant function. Like first exercise problem. Like first exercise problem, f of n here equals to C. It's a constant function. See here, first exercise problem, f of n is 1. It's constant. Okay, constant means degree 0. So now you know what is A, it's equal to 1. What is B, it's equal to 2. What is D, it's equal to 0. So what is the relation between A and B power D? A equals 1. B power D is nothing but 2 power 0 is nothing but 1. So relation is A equals to B power D. A equals to B power D. So which case? So A equals to B power D means as the second. T of n belongs to big theta of n power D log n. Okay, so got it. So T of n belongs to what? Big theta of n power d. Here d is 0. So I've written n power 0 log. So n power 0 is nothing but 1. So therefore T of n belongs to big theta of log. Got it? So order of growth for this exercise problem 3 is logarithmic. So clear? Seems to be easier, right? Rather than solving, we can take an advantage of Master's theorem. Clear? So it's very important, very easy. In exam, you will be given some recurrence equation, okay? And you will be asked to determine order of growth. If initial condition is given, better solve it. But if only objective is to determine order of growth, not to determine exact basic operation count, okay? Not to determine exact basic operation count, only to determine order of growth means to make use of Master's theorem. So time will be saved. Okay. So now let me have a look at one more problem. Okay. See here, recurrence is t of n equals 7t of n by 2 plus 18 n square. It's very clear a equals 7, b equals 2. D is degree of f of n is quadratic, is 2. So what is a 7? B to the power d, 2 raised to 2, 4. So what is relation between a and b power d? A greater than b power d. If a is greater than b power d, I think is the first case. Sorry, third case. A is greater than b power d, third case. T of n belongs to what? Big theta of n log to the n. T of n belongs to big theta of n to the power log a base b. See here, T of n belongs to big theta of n to the power log 7 this. Yeah, it's very simple. Just analyze. Okay. In place of A, it is 7. In place of B, it is 2. If we can't tell what is log 7 to best, retain as it is. Got it? If we can't tell log 7 to best, retain as it is. So one more problem. See, in this recurrence, A is 9, B is 3, D f of n is 4n square plus 3n to the, sorry, f of n in this case is 4n to the power 6 plus 3n to the power 5 plus 2n to the power 2 plus 1. So degree of this f of n in this case is 6. So what I'll find? A less than b power d. A less than b power d means first case. T of n belongs to big theta of n power d. So T of n belongs to big theta of n power 6. So with this, I'll wind up my session. Thank you for listening.